Hello, I welcome you to the channel Microwave Testing, which is focused on the non-destructive testing using microwaves. If you want to learn the basics of this method, then you are right here. I welcome you to our fourth tutorial on the basics of microwave testing. We start with an everyday experience. When we look around, we can see different objects. For example, this champagne glass, and we can distinguish the materials, that is the glass, the champagne or water, and the air bubbles. We can do this because of their different refractive indices, and which leads to reflection and refraction. So it is with microwaves. However, instead of refractive index, we characterize the material mostly by its permittivity or dielectric constant, which is just the square of the refractive index. So as all sensors and detectors, microwave testing also responds to just one feature, and that is the permittivity. By the way, microwave testing also responds to conductivity, electrical conductivity and exchanges. So far, we had seen the spiral that occurs when we move the transmit-receive test head from a faraway air point onto the material surface. And we had learned how the shape of an indication evolves when we move the test head along a line over what we called a defect in air. Today we will learn what happens when we move the test head over the surface of material with a defect inside. First, let's look to some sketches. Here we see the basic situation. We have the transmit-receive test head with the antenna over a plate of some material, for example polyethylene, with a relative permittivity of 2.25. The relative permittivity of air is 1, and it's abbreviated with the symbol epsilon sub r. So the transmitter part is radiating a wave. This wave hits the surface, and where there are changes in permittivity, a reflection occurs. And so a large part of the radiation is reflected into the test head and received by the receiver part. But also a part is transmitted into the material, transferred into the material, and the next change of permittivity is at the backside, and that's reflected again and also incident into the antenna again for evaluation with the test head receiver part. Well, this view neglects multiple reflections. When moving the test head in the distance from the surface, let's think first of a situation where it's very far away. Then we have what we might call the air point, when there's no influence of the material. Then, as we have already learned, we have a spiral when we move towards with the test head and the antenna to the surface, and when we have the antenna just on the surface, we have what we might call the materials point. Now let's come one point further. When we introduce an inclusion, a defect, which at first is far away. Then there is practically no radiation hitting the inclusion and no reflection, so we have the situation as it was before, and the display shows the materials point. Then when moving the test head to the right, all these reflections remain constant. Only the reflection which occurs due to the nearer presence of the inclusion becomes more and more varying. When the distance becomes closer, the amplitude of the reflection from the inclusion is growing, and the phase is more positive. So then when moving to the right, we obtain this, for example, this shape, what we had learned before for the defect in air. And this only adds to the materials point here. This point is just the situation where the test head is over the inclusion, and then the indication goes back to the materials point when the test head is very, very far away. Now we will look to a short experiment which I have prepared. We have here some different materials. We have the glass fiber reinforced plastic part we have seen before already, with a permittivity of 4.5. We have polyamide with epsilon r being 2.8. We have here balsa wood in the middle with permittivity of 1.3. And here we have foam, plastic foam, with unknown permittivity. And we will place the test head on the surface of these materials, GRP, polyamide, balsa wood, then the plastic foam, and we will then do the scan here again to see the signature of the hidden defect, which we had also seen before, the defect which cannot be seen from the top. Now I hold the test head in air, and the display is horizontal approximately 0.03 and vertical 1.2. Well, in the following, the main difference in the displays are in the vertical. So I will only mention the vertical positions in the following. Well, as I said, this is the air point. Now we I place it on the GRP. We see the spiral, and the most deflection is at minus 1.9 for the permittivity of 4.5. Then I go to the air point again and place the test head on polyamide with the epsilon r, the permittivity of 2.8, and we have a display of minus 1.2. Then I go to the air point again and now place the test head on the balsa wood with the epsilon r of 1.3, and now we have an indication of a vertical of 0.7 plus 0.7, and it's more near to the air point because balsa wood contains the volume contains much air, is a very light wood. And now the air point again, and I place it on the foam, and the foam is now approximately 0.95. It's more seems to have more air in it than the balsa. And here we are in the air point again. Now I place the test head on the GFRP again, and I will move it on the now on the along a line across the defect, the hidden defect. And we see the deflection. It is not much. The reason for the only small deflection is that I had to switch the oscilloscope to a rather insensitive display in order to have the air point and all the materials points on one screen. If required, one can switch the oscilloscope to a more sensitive display and have the deflection indications zoomed. In this diagram, we see the permittivities of the vertical deflections of our measured material points. We can use it to determine the unknown permittivity of the foam. From the measured value plus 0.95 on the horizontal axis, we get a value of 1.1 to 1.2 for the permittivity of the foam on the vertical axis. By the way, in the description to this video, you find a link to a table in which permittivities of various materials are given. So far for today. See you next time. If you liked this video, please share it. Goodbye.